Welcome you all again for the thermodynamic lecture series. So in this today's lecture, we are going to solve a few more problems on polytropic process. So before getting into the problem, so we need to know what is the state of the steam. Okay, so there is the condition of the steam or the quality of the steam we need to identify. So for that, we all know that they are having three different conditions or quality of the steam is available. The first one is wet steam, and second one is dry steam, and third one is your superheated steam. Okay, so how these qualities are classified? Okay, so these classification, how these qualities are classified is detailedly explained in the previous lectures. If you have any doubt, you can go through the previous lecture. Okay, so just I am recalling that. So if we say the given specific enthalpy is lesser than the specific enthalpy of saturated vapor, then it is called as a wet steam. Okay, when a given specific enthalpy which is equal to saturated specific enthalpy of vapor, then they are called as dry steam. Okay, so here x value which is equal to 1 here. Okay, then if we say it is a superheated steam, then the specific enthalpy of the saturated vapor is lesser than your given enthalpy. Okay, so this will be applicable for your specific volume also. Okay, for instance, so the given specific volume is lesser than the saturated specific volume of the vapor, then it is called as a wet steam. When the given specific volume and the saturated specific volume of the gas which is equal, they are called as dry steam. When the saturated specific volume of the vapor which is lesser than your given specific volume, then it is called as your superheated steam. Okay, since the same condition will be applied for your specific entropy also. When coming on your temperature, we should say it is a saturation temperature. Okay, so we all know what is saturation temperature. So at this point the phase changes will occur. So in this saturation point, the given temperature is lesser than your saturation point, the steam will be of a wet steam. Then your given temperature which is equal to the saturation temperature, then it is a dry steam. Then the saturation temperature is lesser than your given temperature, then it is known as the state of the steam is your superheated steam. Then, so based on the qualities wet steam, dry steam and superheated steam, we should know some of the basic properties and how to use the formulas for your basic properties. Okay, so first one is your specific enthalpy, the unit is kilojoule per kilogram. If we say the steam is wet, the condition is the given specific enthalpy is lesser than that of your saturated specific enthalpy, then H is equal to Hf plus X into Hfg. Okay, where H is your specific enthalpy at liquid stage. Okay, so this is your combination of both, so liquid and gaseous vapor. Okay, so X is nothing but your dryness fraction. Okay, what is meant by dryness fraction? That is the amount of, that is the mass of vapor present in the total amount of the steam. Okay, so that is mg by mf plus mg. Okay, X equal to mg by mf plus mg. Then if we say dry steam, I already told that X equal to 1. You substitute your X equal to 1, then it becomes h of g. Okay, so h of g can be written as hg minus hf. So plus hf and minus hf will get cancelled. Again the term will be h is equal to hg here. For superheated, so h is equal to hg plus cp, that is the constant pressure of the superheated temperature values. Then your T superheated minus your T saturation temperature, the difference between your superheated and saturation temperature. For specific volume, again for a wet condition, V is equal to Vf plus X into Vfg, and for dry steam it is V is equal to Vg, and for superheated steam V is equal to Vg into T sup by T saturation. And also for your specific entropy, S is equal to Sf plus X into S of G, where S equal to Sg. Here for superheated, S is equal to Sg plus Cps of ln into the ratio of T sup by superheated temperature divided by your saturation temperature. And also work done. So we also know that the flow work is equal to P into V. So that is work done is equal to P into V for all the three cases. But this volume, the specific volume will be varied according to these three different conditions. And also know the specific volume is instead of the reciprocal of your density, or otherwise density can be written as 1 by your specific volume in all the three cases of your quality of the steam. Then the specific internal can be determined by H is equal to U plus PV relation. So with this we can write U, specific internal energy U is equal to H minus PV. So this H, the specific enthalpy and the specific volume will be depend on these formulas. What are all the state of the conditions? So corresponding state of the conditions, this internal energy will vary, but the formula for the internal energy for all the three cases are same. Okay. Problem number 21. 1 kg of steam initially dry saturated at 1.1 megapascal. So in this problem the mass is given, the mass is 1 kg of the steam, it is initially dry saturated. Okay, so at the initial condition x1 is equal to 1, that is dry saturated, and the pressure P1 is equal to 11 bar, that is 1.1 megapascal. Expands in a cylinder. Okay, here it is expansion will happen. How the expansion will happen? That is cylinder following the law PV power 1.13 is equal to constant. That is, it expands by following the process of polytropic. As we say, PV power 1.13 is equal to constant, so N is equal to 1.13. So the polytropic index N is equal to 1.13 in this case. The pressure at the end of the expansion is 0.1 megapascal. Okay, so that is 1 bar. After expansion the pressure P2 is 1 bar. So determine the final volume V2, final dryness fraction X2, and work done, change in internal energy, and the heat transfer. So that is V2, X2, work done as W, and change in internal energy as delta U, and heat transfer as Q for your polytropic. So for that, the given condition is P1 is equal to 11 bar and dry saturated. So I am going for the steam table. At the pressure table, at pressure P1 is equal to 11 bar, I have taken the values of Vg, Hg and Sg because it is saturated. So we have to take the saturated vapor. So Vg, Hg and Sg as V1, H1 and S1. Okay, so V1, H1 and S1 as V1 is equal to Vg1, H1 is equal to Hg1 and S1 is equal to Sg1, as we all know, since it is a dry saturated steam at this case. And we know it is a polytropic process, so we can write P1 V1 power N is equal to P2 V2 power N. So we know P1 and we know V1 from this case. Substitute all those values and the polytropic index N is 1.13. Okay, so then V2 is 1.48 meter cube per kilogram. So this is your specific volume, but in the problem they have asked final volume. So mass is given, so you multiply with the specific volume with your mass, you can get the total volume V2 is equal to 1.48 meter cube, since the initial mass is 1 kg. And again at the pressure P2 is equal to 1 bar, again I am going for the pressure table. At 1 bar pressure I am taking out Vg value. Okay, so taking out the Vg value, because we know V2 from the polytropic relation, V2 is equal to 1.48 meter cube. So I am comparing value will be Vg. So Vg is 1.6938. Okay, so again the condition of the steam is wet here, because the given V2, so given V2 is 1.48, which is lesser than 1.6. So V2 is less than Vg2. So the condition of the steam is wet. In this case I am taking out Vf2, Hf2 and Hfg2 to find out your X2 value and also H2 value. So V2 is equal to Vf2 plus X2 into Vfg2, as we all know, to find out X2. So since it is a polytropic process, from P1 V1 power N is equal to P2 V2 power N, we have find out P2 in the earlier cases. So substitute those values to get X2 is equal to 0.874. And also we know that to find out the specific enthalpy at wet condition, H2 is equal to Hf2 plus X2 into Hfg2. So substitute all those values of Hf2 and Hfg2 in this case, and X2 as 0.874 to get H2 is 2390.9 kilojoule per kilo. And work done. So work done for your polytropic process formula as work done is equal to P1 V1 minus P2 V2 divided by N minus 1. So substitute all the terms in terms of pressure in terms of kilopascal. We know all the values to get work done per unit mass as 362.53 kilojoule per kilogram, but in the problem the mass is given as given, so you have to multiply with mass to get the net work done, that is work done is equal to 362.53 kilojoule, because there is no change here because the mass is 1 kg as given. Then change in internal energy delta U. So delta U is equal to U2 minus U1. So we know H is equal to U plus PV. So from that relation we can derive U2 as H2 minus P2 V2 and U1 as H1 minus P1 V1. So substitute all those values. So one point we have to keep it, remember here, substitute this pressure values in terms of kilopascal. Okay, then delta U is equal to minus 341.67 kilojoule per kilogram. But we need internal energy. This is your change in specific internal energy, so we need change in internal energy as in the problem. So you have to multiply with mass. Again there is no change because since mass is 1 kg, so the change in internal energy is minus 341.671 kilojoule. Then we need to find out Q. So as from the first law of thermodynamics, Q is equal to W plus del U. So we know W value and delta U value. Substitute those to get the heat transfer Q is equal to 20.86 kilojoule. So in the other way also we can find out this heat transfer. So Q, we know the formula Q is equal to mCp into m into H value. Okay, so m into H2 minus H1. So in that value also we can find it out. Okay, so as a result, the final volume V2 is 1.48 meter cube, and the dryness fraction X2 is equal to 0.874, and work done is equal to 362.53 kilojoule, and delta U is equal to minus 341.67 kilojoule, and Q is equal to 20.86 kilojoule. Problem number 22. Steam at a pressure of 15 bar and 250 degrees Celsius expands according to the law of PV power 1.25 equal to constant. Here is also steam. At the initial pressure P1 is equal to 15 bar and the temperature T1 is equal to 250 degrees Celsius. It follows the law PV power 1.25 equal to constant. So this relation itself says that this problem behaves the polytropic process, and with the polytropic index of N is equal to 1.25 to a pressure of 1.5 bar, pressure P2 is equal to 1.5 bar, and evaluate the final conditions, work done, heat transfer and change in entropy, and the mass is also given. The mass of the system is 0.8 kg. Here we need to find out the final conditions, that is the condition of the steam we need to identify, and work done, heat transfer and change in entropy for your polytropic. So for that, add the saturated water in the steam pressure table at pressure P1 is equal to 15 bar, and the comparing value of their saturation temperature is 198.3 degrees Celsius, but the given temperature is 250 degrees Celsius, so which is lesser than your saturation temperature. So that is, the given temperature is less, given temperature is more, the saturation temperature is less. Okay, so saturation temperature is lesser than your given temperature, then the condition of the steam is superheat. So you go for your superheated steam table, take your specific volume. So at pressure P1 is equal to 15 bar and temperature T1 is equal to 250 degrees Celsius. So specific volume V1 is 0.1520 meter cube per cube. And again you go for your specific enthalpy of your superheated steam table. Pressure P1 is equal to 15 bar and temperature T1 is equal to 250 degrees Celsius. You can take H1 as 2923.5 kilojoule per kilogram. Again you can go for your specific entropy of your superheated steam table. At pressure P1 is equal to 15 bar and temperature T1 is equal to 250 degrees Celsius. You can take the entropy S1 is equal to 6.710 kilojoule per kilogram Kelvin. Since it is a polytropic process, so we can apply the PVT relation, that is P1 V1 power n is equal to P2 V2 power n. So we know P1 V1 and also n P2 and also n here. Only one unknown term is V2 here. So solving this simple relation, you will get the specific volume V2 is equal to 0.959 meter cube per kilogram. And at the second state P2 is given as 1.5 bar. So you go to your pressure table, P2 is equal to 1.5 bar and take volume, since we have find out volume in the previous case. Okay, so V2, so in the comparing value you have to take it out VG here. So VG is, VG2 is 1.1590 meter cube per kilogram. So V2 is lesser than VG2. V2 is 0.959 meter cube per kg, which is lesser than your VG2. So the condition of the steam is wet in this case. Okay, so if the condition of the steam is wet, you need to find out the dryness fraction X2 and also H2 and S2. So for that I am taking all the values from the steam table, that is VF2, HF2, HFG2, SF2 and SFG2 from this corresponding 1.5. So again V2 is equal to VF2 plus X2 into VFG2. So we know V1 is P1 V1 power n is equal to P2 V2 power n. So from that relation we have already find out V2. Okay, so substitute those value. Only one unknown term in this case is X2. So X2 is 0.827. So since the condition of the steam is wet in the second case, so for the specific enthalpy formula will be H2 is equal to HF2 plus X2 into HFG2. Substitute all the values of HF2 and HFG2 from your steam table. Then your H2 will be 2308.25 kilojoule per. And in the similar way you can find it out S2. S2 is equal to SF2 plus X2 into SFG2. Substitute all those values what we have taken at the corresponding pressure of P2 is equal to 1.5 bar from the steam table. Then you can get S2 is equal to 6.22 kilojoule per kilogram Kelvin. And the change in entropy here, that is change in specific entropy, because we have find out the specific entropy here. The change in specific entropy is S2 minus S1, that is minus 0.49 kilojoule per kilogram Kelvin. But in the problem they have asked about change in entropy, so you have to multiply this with your mass. Mass is given in the problem, right? So the change in entropy as change in specific entropy into your mass, that is 0.49 into 0.8, that is delta change in entropy as delta is equal to minus 0.392 kilojoule per Kelvin. And as we all know, the polytropic work done will be work done is equal to P1 V1 minus P2 V2 divided by N minus 1. Substitute all those values here. Substitute the pressure in terms of kilopascal to get the work done per unit mass as 336.6 kilojoule per kilogram. But mass is given in the problem, so you multiply with mass, you get the total or net work done will be 269.28 kilojoule. So we need to find out Q. So Q is equal to W plus delta U. Either we can find it out, or otherwise we can find it out. Q is equal to MT into H2 minus H1. Okay. So we know mass and we know H2 values and H1 values. Substitute those values to get Q is equal to minus 492.2 kilojoule. So as a result, the final condition of the steam is wet. Second state, the condition of the steam is wet. So X2 value will be 0.827 and the total work done or net work done is 269.28 kilojoule, and the heat transfer Q is equal to minus 492.2 kilojoule, and the change in entropy delta S is equal to minus 0.392 kilojoule. Thank you.